Okay, so welcome back. I hope everybody had a good break. And we're going to pick up where we left off last time. Pretty much, I'm going to do a little bit of a sort of a rewind review like I always do. So first, I'll note just, I'm sure you've noticed we have a lot of pages left to cover. A lot of what remains to be covered is stuff that we don't need to cover in great detail, and it's just there to kind of give you some geometric intuition, and so we'll spend the time that we can. There's a little bit of it that I'm going to officially absolve you of. It's not part of the course. It's supplemental. It's kind of cool when we have time, and we just don't this semester, and that's how that works. And then some of it is supplementary examples that I think are nice to do when all the material is done. Again, when time permits, and it didn't, but I have some video recordings that I can give you that I recorded actually during the pandemic that go through all of those supplementary examples in detail, so we'll get that resource to you. Yeah.
But that's like covered on our exams and stuff.
Yeah, it's fair game. Yeah, that's right. And in fact, it's all of that stuff is it's stuff we've already covered. It's just additional examples of stuff we've already done a while ago.
Okay.
Yeah. Okay, so let's dive in and get going. Okay, so Stokes' theorem, reminder. We had to worry about what we mean by boundaries, and in particular what we mean by the orientation that's implied by that word. And just remember, this is on y'all at this point. When you hear the word boundary, that means oriented according to this convention, or depending on the context, whatever the appropriate convention is. Okay. That noted, we made this powerful observation last time that boundary circulation is an accumulating quantity. Right? Really big observation. Now, not too hard to see. You've got this common edge and, opposite directions on the same edge. They have opposite signs. They cancel. It's the usual story. Leaving us with this powerful conclusion. We have an accumulating quantity. And as we discussed back in Chapter 6, whenever you have an accumulating quantity, you can view it as being kind of like a stuff. It has an associated density, our stuff being circulation. We're going to talk now about circulation density. This is the formula for it, as it turns out. I'm not going to prove this formula. This is about the details. And I think it doesn't quite make the cut for being... I don't think you should worry about where that comes from. And once you have the associated idea of density, then you can just put it all together. And all of our integral theorems follow this same pattern where you recognize, look, there is some quantity, right? Circulation is a quantity defined on surfaces. We've seen that it's an accumulating quantity. And we've also seen that if you look at little pieces of stuff as being stuff per unit size times size, well, stuff per unit size is that density that we talked about on the previous page. So what we have then, all together, this, again, the usual argument that we always make is that if you want to compute a boundary circulation, you can do so with what at a glance, as I have it written here, appears to be a scalar surface integral. And again, this is just observing that the whole is the sum of the parts, and circulation adds up over the surface, and here we're just adding up over the surface. Stuff per unit size times size. All right. Now, something weird does happen, seemingly coincidentally. A little unexpected, but check this out. We have in ds right next to each other. That is the very definition that we gave in the previous section for the ds vector, which allows us, and again, this is very weird, and I think even this is geometrically unsatisfying. I hope you'll feel a little uncomfortable about this. Even though we were thinking of adding up over a surface in a stuff-like sense, we were thinking of it as being a scalar surface integral, it can be, and arguably should be, thought of as a flux. And like I say, that's weird, it's kind of unsatisfying. But this is the more common way to think of this result is that circulation line integrals are a flux through the surface and a flux specifically of the curl of your vector field. Okay, all right, so let's see an example. Before we get to the example, real quick observation. A common misstatement, common misunderstanding about this theorem is kind of looks like it's saying, if you have any vector line integral, here is a computational alternative. That's not what this is saying. This cannot be just any vector line integral. It says so right here. It's got to be a boundary. This is not a minor little formality technical point. This is a really big deal, again, for two reasons, just like two reasons that we've discussed before. First of all, it's only because we were looking at boundary, specifically boundary circulations, that we get this accumulation feature in the first place. It's got to be a boundary, otherwise I don't even know what the picture is. Okay. Now, secondly, in a more, practical, logistically glaring way, it's got to be the boundary of some surface, because that surface is the domain for my new flux integral. If your curve is not a boundary of some surface, there is no surface through which to even talk about the flux. So it's not that these two integrals aren't equal, it's that this integral isn't a thing. There is no other integral. Right? Okay, so be really, really careful about that. Reminder, I've seen this kind of mistake get made a million times, and I always, my rationale is always, let's make a real big deal out of it in class, and the bigger deal I make out of it, the fewer times I see this mistake happening, and that is true. That pattern holds. So I make a big deal out of it to keep the numbers down, but it is still a tempting thing to kind of ignore this and try to apply Stokes' theorem to a curve. It's not a boundary. And everything that follows from such a misapplication is nonsense. So, careful, right? Please be careful. Don't let that be you. Okay, so let's do one. We want to compute this line integral right here. We got a vector field given. We got a curve given. You could plug and chug, but it's inconvenient. And you could also imagine, by the way, that even for this same curve, you could imagine a different vector field where it would be really prohibitively difficult. And plug and chug is not a good way to do this problem. Okay, let's use our new theorem. Hey, here's an idea. Line integral. How about the fundamental theorem of line integrals? Seems like a reasonable thing to try, right? It's worth a shot. You can try that, but when you try to find the anti-gradient for this vector field, you'll fail. There is no anti-gradient. Now, anyway, it was worth a shot, but anyway, that's another thing to try. Okay, so to use this theorem, as we just discussed, we've got to worry about whether or not our curve is a boundary. So let's look at the picture here. It says that our curve is parametrized like so. Now, y'all will recognize the cosine sine thing, right? There's a circle involved here. The minus sign is a reflection, right? So think through the details. Y'all are qualified to think through what this parameterizes. I claim it is this curve, like this, right there. And as noted, we got to decide if that's a boundary. Well, picture, right? And hopefully not too much of a pitch is necessary for me to argue that this surface right here has the feature that its boundary is my curve. Except we got to worry about orientations, right? This is another thing that's commonly ignored. Very often students kind of forget. Very often students make the mistake of thinking that orientations are no big deal because it's just a minus sign and Who cares anyway? It's just not true. Orientations are a sophisticated, substantial idea. It's an important part of the material that we're covering here. Whether you get the orientation right will probably amount to 4 or 5 points on a 20-point question. It's a really big deal. Right? So we do have to think through the orientations. Okay, so how do we do that here? Well, my curve comes already oriented. If I want to entertain orientations on this surface, let's get it wrong first just to see how that looks. If that were my normal vector, like this, let me zoom. Gesundheit. Then, well, let's play the game, and the boundary of this surface, thumb in the direction of the normal vector and swirls. The swirl would go kind of like this, which would make my induced boundary orientation this way, and it's just not right. So this doesn't work. Okay? So we try it the other way. Let's try it this way. Again, question mark. I hope this works. And, well, let's see here. Thumb in the direction of the normal, and look at the fingers of your right hand. That makes the swirl this way, which has the orientation going the right way. Is that good? Okay, so we have a surface now whose boundary is this curve, and in particular, that surface is this disk oriented like so. Oh, whoops. Let's see here. There we go. Okay. So, right. Good deal. Our curve, our original curve, over which I want to compute my integral, that curve is the boundary of this surface. Being as it is a boundary, again, that's the big sticky wicket on whether we can use Stokes' theorem. And Stokes' theorem tells us that the boundary circulation is a double integral, a flux integral of the curl. We've got ourselves a normal vector already established. And basically a bunch of details to follow. Clear off the mess. You do have to compute the curl. Right, the curl ends up being 0, 0, 2. Specifically, that is the curl, don't forget, of the vector field we were given, the vector field whose circulation we're interested in. Make sure you can compute that, right? That's just a formula. It's just a formula. We've been computing curl since chapter 3, but make sure you can do that as a little formula, various partials, and etc. And then look how easy the resulting integral becomes. And again, no guarantee this will always happen, but it's turned into an integral that's, in this case, easily computable. No messy calculations required. Yeah.
Can you explain why you didn't put the minus sign for the boundary?
Because this surface is, this curve is literally a boundary.
Okay.
Right? And now I hear where you're coming from, right? It's tempting to say, yeah, but it's going clockwise, isn't it supposed to be counterclockwise? Yeah. Well, there kind of is a minus sign in the fact that, if you look at this coordinate right there, it is a minus.
Oh, so it's like if you flip it 180 degrees, then it is going to the left. And
yeah, that'd be one way to say it. Okay. Yeah, sure. Right. Is that cool?
Yeah, thanks.
Okay, yeah.
I was just wondering, for the parameterization, why we have the negative on the sign and not the sign if it's plus?
This was given.
Oh, it's just...
That's given. That's what the curve C is.
Okay.
Yeah. Just the statement of the question. All right. Okay, so that's an example. Now, these next few pages, again, are here just for sort of intuition purposes. I think this is really useful. I hope you like it as well. We'll see. First, a flashback to when we were talking about the fundamental theorem of line integrals. I made this observation that while little bits of change can be thought of as change per unit size times size, and as such, change per unit size is our change density, right? That was a point of view that we took. If you rewrite TDS as dx, and then if you ask, okay, how would I make sense now out of this equation? How would I make sense out of change not related to size, but related to oriented size? Remember the idea of this dx vector. It tells you the size, but it also tells you the orientation. It's got t built into it. If this is oriented size, then a reasonable take might be, a reasonable sort of semantical choice might be that the thing that you multiply by oriented size, maybe we would call this the oriented density. Right? It's just language, right? It's just a semantical choice. But I think it's a pretty reasonable choice given the following. What do we know about the gradient vector? Well, among other things, it tells us how steep the mountain is. Right? It tells us how steep the graph of the function is. So again, my little metaphor is how steep is the mountain. But if I'm on the side of a mountain and uphill is that way, and so there's the mountain's going up like that, yeah, the mountain's steep. But if I go this way, I'm not going to detect that. I'm not going to, right? I have to actually go in the right direction to experience that steepness that the gradient is describing, right? So the gradient vector is telling me two things. It's telling me how steep the mountain is, sure, but it's also telling me in which direction is that steepness happening, right? And so it's telling you, in some sense, both the magnitude and the direction that steepness is happening, and how fast, in what way is the function changing. The nature of how the function changes locally has both a magnitude and a direction. So I think this is a reasonable take to call this oriented change density for that reason. And now with all of this in mind, let's look at the very analogous situation, surprisingly analogous situation, talking about Stokes' theorem. So again, accumulating quantity of stuff called circulation. There's our density, because that's stuff per unit size that I would then multiply by size to get stuff. We've already observed that you can group these two together like so. And notice that this ds vector now is telling us two things. It's telling us the size, ds, yeah, sure, absolutely, that's the magnitude of the ds vector, but it's also telling us the orientation. It's telling us how that area is sitting in space, how it's sort of arranged in space. So with that in mind, how am I going to make sense now out of the curl? This is what I multiply by oriented size to get stuff, d sigma. And so again, I'm going to want to call this an oriented density. And quantity being circulation, this is oriented circulation density. And I know that's a lot. Okay, so it makes sense, though, in the same way that gradient does. In the same way that gradient is telling you both how much the function is changing and in what direction that change is happening. Likewise, curl tells us two things. I got my colors confused. Okay, yeah, red first. So it tells me how much of a rotation of the fluid there is. The magnitude of the curl is going to tell me how much is the fluid rotating. How strong is the tornado? Right? And it's also going to tell me the direction. In particular, it's going to tell me what direction does the axis point that rotation is around. If you think about it, right? You've got a rotation of the fluid. Fluids can rotate like this. This would be around a vertical axis. But fluids could also rotate like this, around a horizontal axis, or around a different horizontal axis. The direction that the curl points tells you what direction the axis is. Is that cool? So this is I think a really important, if you're going to have a good understanding of what curl is, you need to understand what does its magnitude mean. That's telling you how much rotation is happening. And you got to know what the direction that it's pointing means. It's telling you what direction the axis is. So drawing a picture out of that, the curl being a vector like that, the magnitude here tells me how strong is the rotation, how strong is the hurricane, how much rotation is happening, and the direction. Let's see here. I'll use blue again. The direction is telling you what the come on. Close enough. What is the direction of the axis that it's rotating around? Is that cool? Okay, now what follows is just this is not a proof of anything, but I think this is good again for intuition. What's the deal with this curl dot in, and why? How can I buy the idea that curl dot in is a relationship between size and circulation, right? In other words, why is curl dot in detecting what I'm calling circulation density? Why dot the curl with the in? So now again, not to prove anything, but just to kind of, see this kind of play out in action. What I have here is a couple of scenarios. Here we have a curl vector. Right, we got a fluid flowing around. And we have a little piece of surface. Here, let's just look at this top example here, looking at this little piece of surface. And you can see I've got its boundary curve indicated, and I've got its normal to the piece of surface, little normal vector indicated. Right? And now I'm going to start by asking, to what extent is that fluid circulating around this boundary? Now, this just, use your geometric intuition. To what extent is this fluid flowing in the same direction that boundary curve is? And I'm going to say, yeah, quite a bit. I mean, it's like the fluid flow is tracking the boundary curve the whole way around. So you're going to expect, we should expect, that there is a significant amount of circulation happening there. If I were to compute that line integral around that little piece of surface, you would expect a significant amount. Now, how does curl dot in pick that up? Well, curl is that way, in is this way, and this dot product, again, significant. Right? Those two vectors that we're dotting are pointing in the same direction. And I'm going to appeal that the fact that these circulations are aligned, right, is geometrically simultaneous with those vectors being aligned. The more that I rotate, like if I were to rotate this piece of surface so that it kind of gets a little out of whack with the rotation of the fluid, well, then the normal vector would be rotating away from the curl vector. So we'd be getting less circulation, and there would be less dot product. Yeah.
And that's like, geometrically speaking, that's like the angle at which you're rotating is based on like the cosine.
Yeah. That's right. There's a cosine in the dot product. Yeah, absolutely. Yeah, totally. So just for the kind of the extreme example the other way, I mean, if you rotate it substantially around to where, so for example, here you can see I've rotated the little piece of surface around to where, look, the fluid is rotating like this, but the curve is rotating in a completely different way. This fluid is not flowing along this boundary. Not. Right? I would expect here to have very little circulation. And again, that is picked up perfectly by the fact that the curl is pointing that way, but the normal is pointing this way, and this dot product is not going to be very much, if any. These pictures always kind of, the extent to which the flow is along a boundary is always coincidental with the extent to which the curl is along the normal. So again, just for geometric intuition, for your consideration, this doesn't prove anything. Okay, let's see some physical examples. This first one I'm going to be a little quick with. We've already kind of talked about this. I just haven't put it into context. I'm going to remind you that when we're talking about a two-dimensional fluid, we have a fluid, for example, let's say kind of like this. You imagine this again being the flow of water on the surface of a little stream or something, and you have some leaf that's floating, and the velocity of the water is going to push the leaf downstream. Yeah, sure. But check it out. It's being pushed more on this side than on that side. You expect this leaf to kind of be rotating like this, right? Well, curl is what is going to tell you that rotation. And if you were to get algebraic about this, if you were to actually write down a formula for a vector field like this, and if you were to compute the curl, you would get a positive value, positive indicating counterclockwise. Okay, so that's old news. Three-dimensional curl does kind of the same thing. Now, curl, though, is a vector. We have to change the metaphor. I don't just have a two-dimensional sort of plane that the fluid is sort of flowing through the plane. Now I have 3 dimensions. I like to think about air as being my fluid, like here in the room. I can't talk about leaves. They'll just fall down on the ground. I like to imagine little balloons that are perfectly weighted. I'm sure you all have all had this experience that you have helium-filled balloons, and then a couple days after the party, they're not on the ceiling anymore. They're just kind of floating. And there's that perfect couple of hours where they're just perfectly weighted. A couple hours later, they're on the floor, right? But there's that moment, that just right moment where they just kind of perfectly weighted and they can just kind of flow around, right? So in the same sense, as usual, the vector field tells you how the balloon is going to be moving, but curl tells you about the rotation. Curl tells you the axis around which the rotation will be happening, and in some sense, how much it's going to be rotating. And again, you got to worry about units, and if friction of the air against the balloon is what's making it rotate, then we'd have to, if you wanted to get real particular about it, we'd need to know what's the coefficient of friction there and what's the moment of inertia of the balloon. There's a bunch of details that aren't our problem, right? But the more the fluid rotates, right, the more the curl says how much the fluid is rotating, the more the fluid is rotating, the more the balloon will be rotating. All right, so just like in 2 dimensions, just 3-dimensional rotations. Okay. All right. This is what we're going to skip a lot of, magnetic fields. It's not officially part of the course. It's a nice supplement when we have time. This semester we don't, so be it. That said, it is in your future if you're an engineer. And so I'm just going to say a couple of quick things about it. When you have a flow of charged particles, we call this a current field. And so, for example, something like this, flow of charged particles. Physical reality, weird though it may seem, is that a flow of charged particles creates a magnetic field. Something kind of along these lines. And we use B to represent that. So current creates a magnetic field. Very strange. Physical reality. Well, these two vector fields, the current field and the magnetic field, relate in strong ways. And one way to talk about that relationship is this. Another way to talk about the relationship is that. You'll recognize this little square of equations. We wrote down a kind of a little square of equations when we were talking about electric fields and gravity and that kind of stuff, right? Light bulbs, right? There's strong analogies there. This time, though, everything's a little different. It's not Gauss's divergence theorem at the bottom. It's Stokes's curl theorem down here at the bottom. And the punchline is, we don't have time for the details, Stokes's curl theorem is the thing that allows you to connect this version of Maxwell's fourth equation with this version of Maxwell's fourth equation. They look very different on the page. Current being magnetic circulation doesn't seem to be particularly related to magnetic curl being a current field. They sound totally different, but they're immediately connected by way of Stokes's curl theorem. So neat fact to know, and when y'all take your appropriate physics classes about magnetic fields and current and stuff like that, take another look at this. This will help. Okay, another little quickie. Oh yeah, question.
So like in this class, if we have to like do something with like magnetic fields or something, would we be given these equations?
Yeah, I don't have any plans to do any such thing. Yeah, I don't think that's going to happen. This is a supplemental.
Okay.
Yeah. Nothing to worry about in Math 219. Yeah. Right. Okay. Y'all might remember this from Chapter 6. This is literally a copy-paste from Chapter 6. And the big idea was that Green's theorem is exactly what we needed to connect various little observations. So, we'd made certain observations about path independence, and we'd made various observations about, if you have an integral expression that's always zero no matter what region you're talking. How could it possibly be that an integral is always zero for every possible region? Well, the only way is possible is if the integrand is zero itself. Okay? So Green's theorem is the thing that connects these blue ideas to these orange ideas, and therefore Green's theorem is what allows us to draw this conclusion here, that if you want to decide if your vector field is a gradient, in other words, is there an antigradient? You take the curl, you see if it's zero, and that answers your question. Okay. I stated a three-dimensional version of this and apologize for the fact that we didn't have the appropriate tools to be able to fill in the blanks, but we do now. Stokes's theorem is, again, the thing that makes the analogous connection, the thing that connects related ideas to path independence and these ideas here. Stokes's theorem fills in that missing link, and again, we have our little local test. If you want to know if a three-dimensional vector field is or is not a gradient, is or is not path independent, compute the curl. See if you get zero. That decides the question. Okay. So, again, this doesn't give us a new result. We already wrote this result down back in Chapter 6, but now we can see why, and Stokes's curl theorem was the missing ingredient to make it work. Okay. All right. Moving along. This is a new idea. This is a really important new idea. This is one of my I don't want to say pet topics, but this is one of my favorite topics. I also find that this topic is extremely underrepresented in multivariable calculus courses. We're going to see momentarily this idea I'm about to describe called surface independence. It's a lot like path independence. We've already seen how path independence is a very natural idea, really important idea. Surface independence is the same idea, just applied in a different setting. And yet, mysteriously, most multivariable calculus books never mention surface independence. Even though it's computationally very powerful, very useful, it just doesn't come up. And I think that's weird. So this idea is part of Math219. This is something you're responsible for. So let me start off with where surface independence comes from. It comes from analogy with path independence. Let me remind you what path independence means. Path independence considers a scenario where I have two curves, C1 and C2. Those two curves having the same boundary points. That means they start at the same point, they end at the same point. Okay, so you've got to have that shared boundary to be able to talk about the property that path independence holds. If a vector field is path independent, what that tells us is that the C1 green line integral and the C2 blue line integral will always be the same. And again, restriction, these two curves, C1 and C2, have to start at the same point, have to end at the same point, so they have to have the same boundary points, in other words. Okay, now another way to say it, same thing, is a vector field is path independent if when I look at the sort of the whole curve going all the way around, that closed line integral is 0. Now, this is an equivalent statement because if green equals blue, and if this orange curve is green minus blue, their difference, the difference of two things that are the same, is 0. Okay, so two different takes on the same fundamental idea of path independence, and I hope this all looks familiar. We've seen this a while ago. What I'm going to do now is kind of copy all of these ideas one dimension up. We're not going to think about curves and shared boundary points. We're going to think about surfaces and a shared boundary curve. Right? We're not going to talk about line integrals on curves. We're going to talk about flux integrals through surfaces. But other than that, the analogy is going to be pretty much pretty strong. So let's see here. Let's get going. Surface independence considers that I have two surfaces. Again, they have to have now the same boundary, but this time we're talking about a boundary curve. Let me try to get all this on the page at the same time. It's this shared boundary curve, where the green surface, the edge of the green surface needs to be the same as the edge of the blue surface. And surface independence, this property of surface independence would mean that a vector field has this remarkable feature that the green flux and the blue flux would always be equal. And another way to say this is that observing that I can take these two surfaces together, and you got to worry about orientations. There's a minus sign in the orientation here because if I want to talk about this as being a boundary, these two orientations, N1 and N2, you can see one is pointing outward, one's pointing inward. I need the one that's inward to be outward, and so we have to put that minus sign. Punchline, closed fluxes are all 0. So look how strong that analogy is. It's bonkers. Right? It's crazy. The idea of path independence, the idea of surface independence, same idea. The colors tell the story as to how strong the analogy is. It's just that it's about instead of curves with shared boundary points, it's surfaces with a shared boundary curve. It's about flux integrals instead of line integrals. Other than that, morally equivalent ideas. All right. Now, we had a rule talking about path independence. If you want to know if a vector field is path independent, coming up to here, Oh, well, come to think of it, we can just come down to here. If you want to know if a vector field's path independent, you look at curl and see if it's 0. Right? So we're going to have to figure out, is there some analogous rule there? Another way to ask the question, how do I tell if, what kinds of vector fields are they that are path independent? And we've seen previously that gradients are all path independent. Okay, what kind of vector fields are surface independent? It's another question that we need to entertain. So these questions are pretty easily dealt with. This surface independence here, if I were to apply Stokes's curl theorem, let's see here, I'm running out of colors. Let's apply Stokes's theorem to the green surface and to the blue surface, and applying Stokes's theorem applied to the green surface means that, let's see here, I would have a line integral around that shared boundary curve, which is in dark blue here. And if I were going to apply Stokes's theorem to the blue surface, well, then I would have a line integral around that same shared boundary curve. Right? So that seems to suggest we've got a foot in the door, and we just have to ask the question now, what do I need in order to be able to apply Stokes's theorem to a surface? And Stokes's theorem, I'll remind you, let's see, I've got a copy right here. Stokes's theorem applies to a surface when that integrand is a curl. And if you want to apply Stokes's theorem to a surface, you need your integrand to be a curl. So that is the punchline that, what allows this to work is if your vector field is a curl. If your vector field is a curl, it will be surface independent. That's a cool little argument. Okay. All right, and it works the other way as well. By the way, every curl is surface independent, and every surface independent field is a curl. We don't have it's not appropriate for Math219 to talk about that. It's a little too hard to prove that result. Okay, so here's where we're sitting then. We've talked about these ideas. Surface independent vectors are curls, and closed fluxes are 0. I'm going to argue that hypothetically, if we were to encounter a situation where all triple integrals for every domain, every solid domain, all triple integrals, no matter what your domain, of the divergence always gives you 0, how could this possibly be true? What could the integrand possibly be that would make all triple integrals equal to 0? Well, the integrand would have to be 0. That's, again, an argument we've made previously. And so what is it that allows us to connect the green ideas to the blue ideas? If I want to be able to do this, if I want to be able to connect these ideas, I need down here some connection between closed fluxes, boundary fluxes that is, and triple integrals of divergence. And of course, that's exactly what Gauss's divergence theorem does. So again, you're going to notice in the way that this is laid out on the page, it's very analogous to the earlier argument we made where this was Stokes's theorem, and we were talking about path independence. Or previously, before that, this was Green's theorem, and we were talking about path independence in 2 dimensions. So structurally the same argument, just applied in a different setting. Okay, so we now actually have a very powerful computational tool, and here's how this works. Suppose you take the divergence of a vector field. Suppose you get 0. If that happens, if the divergence is 0, that means your vector field is surface independent. And if it's surface independent, that means, actually I shouldn't have erased that. If it's surface independent, that means that as long as you don't move the boundary, as long as you keep the boundary being what it is, you can say phooey to the flux that you were asked to compute and instead compute the flux through a totally different surface. That's the big idea, right? So take the divergence, see if you get 0. If you do, declare surface independence, switch to a new surface. Just make sure that you keep the boundary the same as what it had been. Okay, so let's see this in action. Here's an application question. We want to compute a flux. Yeah, some vector field's given, some surface is given, fine, whatever. Computing a flux. And again, you have a bunch of different options. You could parameterize, it'd be a kind of a pain. And you could try some other tools. None of those are going to work in this case. Here's what we're going to do. As discussed, we're going to take our vector field. We're going to compute the divergence. We get 0. We get to conclude that our vector field is surface independent. That's a big win already. By the way, just from a grading point of view, when the solution to the problem is to use surface independence, just this part alone, again, if surface independence is the solution, right? That part alone is worth substantial points. I can't commit myself to anything in particular, but there's big ideas afoot here. Realizing that in the computation of flux, that divergence is of relevance, realizing that it equaling 0 tells you this powerful tool called surface independence. These are big ideas, and I reward successful application of big ideas with big points. Right? So very little to write down, very good return on investment. Okay. All right, so now let's actually use the surface independence, though. We've got to be careful with the details. Our surface is this right here. Now, there is a landmine here. You've got to be really careful about this. Lots of students make this mistake, and it's one of these deals where the more I make a big deal out of it in class, the less it happens. But it's still a problem. This is still something you need to worry about. You've got to be super duper careful. A lot of people will look at this and think that this is part of the surface, and it's not. This down here is not part of our surface S. Part of the problem, part of your responsibility in solving a problem like this is to interpret the statement of the question carefully and correctly. And notice this business right here, saying z greater than or equal to 0, that's just clarifying which part of the paraboloid we're interested in. It's just telling us which part of the paraboloid. It remains that S is part of the paraboloid. And this stuff down here is not part of the paraboloid. Everybody see what I'm talking about there, right? So this is just, you got to be really, really careful about this. If you misinterpret the statement of the question, oh gosh, look what would happen, by the way. Very easy, tempting, if you were to incorrectly include this, then you'd think, hey, our surface is a boundary. And you'd use the divergence theorem. And that's got nothing to do with the solution of the problem. So you'd be off in left field doing something completely irrelevant to the question. So be super duper careful about that. Again, I like to try to warn you all about landmines, and this is one of them. Okay, so there's our surface, no bottom face. The boundary is this ellipse I've got here in purple. Keep in mind our job when we're using surface independence, our job is to make sure that we don't change the boundary. We've got to keep that same boundary. We just want to find a new surface that has that same boundary. So back to here. What surface can we see that has this same purple curve as its boundary? And there's actually a million options. You could do something ridiculous like that. You don't do anything ridiculous, right? You channel your inner laziness, try to pick the easiest possible surface, and I think it's going to be hard to beat this little flat two-dimensional ellipse in the XY plane. It's got the same purple boundary curve as the blue surface. So that's going to be our S2, which, when compared to the original surface S, that blue flux we want and the green flux that we are going to compute instead have the same value. Is everybody with me? Okay. Last thing I'll say, and I'm going to let y'all read through the rest of the details, but you do have to worry about orientation. So when you look at this original blue surface, it says right here oriented downward, right? And then if you keep in mind the rules about how, thumb in the direction of the orientation, you look at the fingers of your right hand and you think about swirls and stuff, our orientation on our boundary curve is this way. And so when we talk about that we have a new surface, well, we do have to ask, how is this new surface oriented? What direction is that new surface oriented? And let's see here. So our blue surface was oriented downward. Our boundary is in the purple direction. And now you just got to ask, which way would we orient the new surface? And I will observe that if you orient it down, look at the fingers of your right hand and think about swirls and all that, the swirl would go this way, which orients it the correct direction. And if you make the mistake of orienting your new surface upward, it won't have the same boundary orientation and you'll be off by a minus sign. So be real careful with the orientations. We're out of time. We're kind of done with Chapter 7. I should point out super quickly, just for your consideration, oh gosh, if I can get this to cooperate, that this page here is just sort of a reminder that there's this diagram that has a bunch of really good patterns and analogies and stuff like this on it. And then I'll also note that there are 6 examples that follow. These 6 examples are entirely supplemental. I think they're useful, and I'm going to send y'all recordings if you want to hear my explanation of these examples. Those will be on the YouTube channel. Okay, see you later.